In this video, we'll take a look at a few more examples of limits that involve indeterminate forms, that strange and dreaded 0 over 0. And here we have an example of a rational function. The numerator is a fifth degree polynomial, and the denominator is a linear polynomial. So linear polynomials are pretty easy to work with, as are quadratics, but once the degree of your polynomial gets to be large, and for us, what is large? Maybe 4 or 5 in this case, factoring tends to be a lot harder, right? But let's check to see if this actually is indeterminate. So that means we have to take the limit as x approaches 1/2 of the numerator, and since that is one of our elementary functions, that is, it's a polynomial, then we can go ahead and try to evaluate it. So let's evaluate this. So 2 times, now 1/2 to the 5th power is 1 over 32, minus 1/2 to the 4th power is 1/16, plus 2 times 1/2 to the 3rd power is 1/8, minus 1/2 to the 2nd power, that's 1/4, 12 times 1/2, so that's, I'll just write that down, plus 12 times 1/2, and then minus, now 6, right? So let's start by simplifying the fraction. So 2 times 1 over 32 is 1/16, and then I have a minus 1/16. 2 times 1/8 is 1/4, and then I have a minus 1/4. So wow, everything's kind of balancing out here. And then 12 times 1/2 is a positive 6, and then I have a minus 6. So yes, in fact, the numerator approaches 0 as x approaches 1/2. What about the denominator? So the limit as x approaches 1/2 of the linear function 2x minus 1. So that's 2 times 1/2 minus 1. 1 minus 1, that's 0. Yes, so this is that form that we don't like, right? So then what do? Well, for polynomials, the usual trick is to factor, right? The question is this factorable? It has to be, and the reason why we know it has to be factorable is because when we plugged 1/2 in, we got a value of 0. So our factor theorem tells us that 1 root is x equals 1/2, and then there has to be a factor that corresponds to that root. But I think just to illustrate yet another process from algebra that's helpful, if you notice this factor here, right, or this 2x minus 1 also, when evaluated at 1/2, also gives 0. So what that means, right, that implies that this polynomial, this numerator, is actually divisible by 2x minus 4. So I should be able to divide our 5th degree polynomial by this linear polynomial and just I won't get a remainder, and I'll get a quotient. So I want to illustrate long division here. So using long division, because in some instances it's another very useful tool, right? And it's useful not just in the context of limits, but since our goal is to reduce this rational function to its lowest terms, one way we can do that is through long division. So let me remind you of the process. We are going to take this leading term, this 2x to the 5th, and divide it by 2x. And when I do that, I am left with x to the 4th. So that's going to be my first term here. And then I take my x to the 4th, multiply the entire divisor, 2x minus 1, and then subtract it from my dividend. So I'm using a lot of the terms that hopefully you may not have used those terms in a long time. But just as a reminder, I want you to be familiar with how everything is referred to. So again, what did we do? We took the first term in our quotient and multiplied the entire divisor, and now I'm going to subtract it from the dividend. Now what happens with the long division algorithm is that the leading term is always going to cancel out. Now, other terms might cancel out depending on the actual polynomial, but for sure we know that this leading term, because when I take my 2x to the fifth minus 2x to the fifth, I'll get 0. But also, when I take negative x to the fourth minus negative x to the fourth, I'll also get 0. But then, so it's basically these terms, but then I have to bring down these trailing terms. So then I'll have a positive 2x cubed minus x squared plus 12x minus 6. And then as long as this power is greater than or equal to this power, right? The highest power in the divisor is, if that is strictly less than this power, then we continue the algorithm. So what's the next step or the next iteration? We're going to divide this by the same 2x minus 1. So when I do that, I'm going to get a positive x squared. So we'll have a plus x squared there. And again, take that new term in our quotient and divide it by the, and multiply the entire divisor. And that gives us a 2x cubed minus x squared, and things are looking good, because when we subtract, again, we're going to eliminate two terms. The 2x cubed is eliminated and the negative x squared is eliminated. So again, we have another 0 there. We don't have to write the 0. We can just simply bring down the trailing terms here at the end. So 12x minus 6. And then same thing, even though this is linear, we can do one more iteration. Even if the powers are the same, then we can do one more iteration. So now we're going to take the 12x and divide it by the 2x, and that's going to leave a constant 6. So that will be a plus 6. And then so when I take my constant 6 and multiply the entire divisor, I'll get 12x minus 6. And another theorem from algebra tells us that once we take a polynomial and divide it by one of its factors, the remainder has to be 0, right? So just to kind of remind you of some of the terms that I was using, in case you want to write them down. This is the divisor. This here is the dividend. This is our remainder. And this is our quotient. So those are all the important terms for the long division algorithm, right? So what does this mean? It means that our original limit, right? So in fact, let me write it down again. It's not fun to write it down. But we have our 2x to the fifth minus x to the fourth plus 2x cubed minus x squared plus 12x minus 6 all over 2x minus 1. Well, when we do that division, what we're left with is the quotient x to the fourth plus x squared plus 6, right? There is no remainder. So essentially we would have, once we write it down, reduced this rational function to its lowest terms. And what are those lowest terms? It's x to the fourth plus x squared plus 6. And now we use our approach. This is an elementary function. I can evaluate it simply by plugging in. So I'll have 1 over 32 plus 1/4 plus 6. And then when you do your arithmetic, we're going to get a final answer of 101 over 16, right? So that's our limit, right? So long division, it's not something that you'll have to do all the time, but it's an important process that you need to remember, because every now and again you're in a calculus problem and you find yourself, oh, I better remember how to do long division, and it tends to be pretty helpful, right? Last example of our indeterminate forms here. So this is number 2 in this video. Let's take the limit as x approaches 2, and it's going to involve a root. So we have root x plus 7 minus 3 in the numerator, and then in the denominator we have x squared minus 4. Let's see, is this indeterminate? So if I take the limit of the numerator, right, if I try to just evaluate that separately, I'll have the square root of 9 minus 3, which is 0. Shocking there, but we go on. So as x approaches 2 of the denominator, what do we have? 2 squared minus 4, and again we get the 0 over 0 form, right? And so what do we do here? Now the root throws kind of a wrench in the whole process. Why do I say that? Well, roots are difficult to work with in some cases. They don't factor easily. You can't really expand them easily. But there is a trick from algebra that involves something called rationalizing. So what we're going to do is rationalize not the denominator, right? But in fact, the numerator, right? So what we're going to do is to rationalize the numerator. And maybe that's some algebra, just like how I did the long division off to the side, I'll do that as well. So how do we rationalize an irrational algebraic expression? Well, the trick is to multiply the top and the bottom by the conjugate of that expression. Now, the conjugate is a fancy word that actually comes from another branch of math that has to do with complex numbers, right? But the form is helpful. It's a helpful term because it follows again, like I said, a pattern from when you're working with complex numbers. But the conjugate essentially is it's almost the same algebraic expression, but the operation that's between the two terms, right, is switched. So instead of the original expression had a minus, and then I'm now going to multiply it by another expression that has a plus. And why do we do that? Because we're going to exploit this nice relationship, this difference of two squares. And in fact, let me do that in a different color, because the relationship is that if you have a plus b times a minus b, you'll have a squared minus b squared. So down here, because you now have the difference of two squares, essentially you're going to get rid of the radical that's in the numerator. All right, so let's see how this plays out. So again, what I'm going to do is just use some parentheses so that you clearly see the order of operations, right? So that's what it looks like. In the numerator, if I take the radical of x plus 7 or root of x plus 7 times itself, the root goes away. So I'll be left with x plus 7. Let me keep that in parentheses. If I take the radical in the first pair of parentheses times the positive 3, I'll have a plus 3 root x plus 7. Now for the other term, and essentially what we're doing is foiling out, right? The negative 3 times the root will be a minus 3 root x plus 7. And then the negative 3 times the positive 3 gives us a negative 9. And what happens is the terms with the radical, they cancel each other out, right? Because you have a positive 3 root and then a minus 3 of the same root. So these terms are gone, right? What happens in the denominator? Well, there is not much we can do. I mean, we could FOIL it out, but the thing is, the trick here is to leave, well, what we should do is get the denominator to be fully factored. And what I'll notice is, this is also a difference of 2 squares, but instead of leaving it in this form, I'm going to leave it in the factored form. So this is going to be x plus 2, x minus 2. Those are the 2 factors from this. And I'm going to write down the third factor that involves the root. So I'm not going to do much in the denominator, because the end goal is, remember what we're trying to do is to factor and reduce, right? And we've eliminated a couple terms in the numerator. Let's see what's left over. We have an x plus 7 and then minus 9. So essentially what we do is we have an x and then a plus 7 minus 9. So that leaves us with an x minus 2 in the numerator. And then the denominator is exactly the same. I haven't reduced the entire function yet. Just kind of rewriting it and getting in that form where now I can see the common factor in the numerator and in the denominator. Now remember, the numerator has a hidden factor of 1, right? So what does this mean? Well, it means that this limit, the original one that gave us that indeterminate form, can be reduced to something that has a 1 in the numerator, and then in the denominator I have one quantity x plus 2, and then another quantity root x plus 7, now plus 3, right? Right, so, you know, again, and what all we've done, now you might say to yourself, well, it's not terribly reduced, but it is somewhat simplified, right? There's still a root, but if you notice, we've been able to get rid of one of the factors of the term in the denominator. And now I am able to say, okay, this is an algebraic function. I can plug in and try to get a number. Now I'll have a 1 in the numerator. This factor here is 2 plus 2, so that's 4. This factor here is 3 plus 3, right? Because we still have our square root of 9, which is 3 plus the other 3. So we end up with, what's that, 6 times 4. So our final answer is 1 over 24. So let me circle that. Right. So hopefully you found these 2 examples illustrative of, again, different strategies or tricks or tools, whatever you want to call it, from algebra that enables us to handle these strange indeterminate forms, right? And algebra, once we're solid on our algebraic skills, it gives us this precise way of evaluating limits. Right, so keep these tricks in mind, and these are not the only times you'll use them. This is kind of our first big use of things like long division and rationalizing. See you in the next video.